So we will get through Chapter 5 today. I'm pretty confident. We're talking about quaternary ammonia compounds. Did you guys go look at any more disinfectants this weekend? Most all of the ones that you can get have these quats in them. And I didn't mean to do that. Most all that have the quaternary ammonia compounds in them. And did any of you go look at the poster? I think I mentioned the poster to you that one of my students did as an independent research project. Did I tell you guys about that? We're wondering about the efficacy and how we loaded plates, just blank, empty Petri dishes, no media, anything, with E. coli, and then looked to see how effective those different wipes were just laying on the surface, and they were basically not effective at all. I just looked at the poster again this morning, just glanced at it. We use Clorox wipes, we use Lysol wipes, we use one other type of wipe, and then she used the isopropanol wipes. So you can take a look at that and see. Most of the ones that you can buy normally at Walmart or wherever aren't very effective in our studies. But what we did find was that if you make them move, in other words, if you apply a wiping motion, they're actually very, very effective at removing organisms on those surfaces. So go take a look at that. One problem with those agents that you can get is that they're all cationic detergents. So you know how a detergent works, right? How does a detergent work? It separates compounds. So what do you know about, what have you seen where you use a detergent? You've all done that experiment where you had a dirty pan and you put warm water in there and the oil kind of floated to the top, right? And then you put some detergent down in the pan, and what did you see happen at that point? The oil kind of dissolves into the water, right? And so the detergent is doing that. And usually detergents have two parts. Usually they have something that's hydrophobic, a region that's hydrophobic, and that part wants to go associate with those oils. And the other part is usually charged, and that part wants to associate with water. And so when the detergent associates with those fats, those lipids that were floating, the hydrophobic part associates with them, and then the hydrophilic part associates with the water, and that makes the molecule dissolve down inside of the water. So that's what those guys that you have at home as detergents. And most all of them have either SDS or SLS, sodium dodecyl sulfate or sodium lauryl sulfate. Those are actually the same thing. They're two different chemical names for the same thing. So if you go read your detergent bottle, I'm pretty sure on most household detergents they write sodium lauryl sulfate, and it's just the size of the molecule. You can go look at it. Anyway, they're these cationic detergents. And, the ones you have at home are anionic detergents, and the quats are cationic detergents. And when you put these guys in the same environment together, then they cross each other out, because the positive charge on the cationic detergents and the negative charge on the anionic detergents interact with each other, and they inactivate each other through those charge processes. So that's a problem of using the quaternary ammonia compounds, because if you took your sponge and made it soapy with water and your detergent, and then wiped the counter down and left any residue, as soon as you go back over it with the quaternary ammonia compounds, they're going to inactivate the sodium lauryl sulfate, and the detergent is going to inactivate those quaternary ammonia compounds. But one of the good things about these guys is that they can react with membrane. They'll destroy vegetative cells and envelope cells, and also they can leave a little bit of a residue on the surface, so in that way they can deal with bacteria that are there. But they're not effective against mycobacterium or endospores or naked viruses, and we've talked about that. Also, Pseudomonas is pretty resistant to these guys. That's just a list of all the chemicals that we've talked about. So as far as preservation of food items or perishable products, we many times use chemicals for preservation. Did you guys go and look about those weak acids? Did any of you look in your cans or canned goods to see if you saw XYZ acid added as a preservative? You guys aren't getting so excited about reading labels as most classes do. I'm expecting to see you this afternoon and this evening in Walmart reading all the labels to figure out which products have weak acids added to preserve them so you don't get Clostridium botulinum. I don't know why you don't want to know, but I'm thinking you should go look. So we do that a lot, adding weak acids. The other thing that we add is nitrates, nitrites. We talked about that, and adding that to beef. Did any of you go ask your butcher why you put so much sodium nitrate in your meat? You tell them you really want the gray stuff so that you know that it's safe and not going to cause cancer for you?
No,
Did you?
we did check all the labels.
You did read the labels on the beef? Did it say? It says sodium nitrate added. Does it say how much?
No.
No. Okay. Could you find any that didn't have sodium nitrate added? None. Okay. That's awesome. Even the white packages
Yeah, we bought it
in a tube?
in the tube.
Yeah. Did it taste good?
Yeah, it's
Tastes all right? Good. All right. Good deal. So we talked about how those higher concentrations of sodium nitrate keep the meat pink. It's actually when you heat the nitrates, they get converted into these nitrosamines right here, and that's what actually causes the cancer. So if you're French and you eat your hamburger raw, French people eat something as a delicacy called steak tartare. I don't know if you ever heard of it. Basically, it's raw hamburger. If you eat it that way, then you don't have to worry quite as much about getting cancer, but you might have to worry about other things. Okay, so you know that we also use low temperatures to reduce the amount of growth of organisms that might cause disease, but those psychrotrophs and psychrophiles, they can still grow in those refrigerated temperatures. But on the other side of the coin, how much do you think you need to worry about psychrophiles and psychrotrophs that might be in your food? Not too much. Why? Our body temperature is 37 degrees. What do you know about these guys? Their optimal growth temperature for the psychrophiles is right around freezing. For these guys is about 25 degrees. And remember that growth curve that looks something like this. For both of them, our body temperature is way outside of their optimal growth temperature. They won't be able to grow down inside of our body. And then I just want to point out this too. The freezing preserves foods by stopping microbial growth, unless we're talking about these guys again. But the book says this. It says some microbial cells are killed by ice crystal formation. And that's somewhat true, but you remember that organism I talked to you about that's called mycoplasma? We put mycoplasma in the domain bacteria, but remember I told you it's a little bit confusing? Remember about it? Tell me about mycoplasma and why it being in the domain bacteria is a strange place for it. Yeah, it's got a really different cell wall. In fact, it doesn't have any cell wall. It's totally lacking a cell wall. And so why is that strange to put it in the domain bacteria?
Because they're either coccus or bacilli.
And so there's two definitions. Bacteria are prokaryotic, and mycoplasma is prokaryotic. And what's the other definition of a bacterium? Peptidoglycan in the cell wall. If you don't have a cell wall at all, then you don't have peptidoglycan in your cell wall. And so that's why it's strange. Anyway, it's a potential pathogen. Mycoplasma pneumoniae can cause pneumonia in humans. And so companies that make vaccines, if they're growing viruses, you need animal cells to be able to grow viruses. And the first job I got after my undergrad was to go work for a company that makes vaccines. And they put me in the viral section of the vaccine production. And so we had to culture animal cells, and most of the viruses we grew in the kidney cells from cows, because when we slaughter a cow, we usually just want the muscle tissue. The kidneys most people don't eat. We could buy the kidneys by the truckload. We could harvest the cells out of them, and then we can infect those with viruses, and we could get the virus back out. But you don't want to include nasty bacterium like Mycoplasma pneumoniae in your vaccine, so we had to test the cells to see if there was any mycoplasma down inside of the cells. And back in that time, basically you had to lyse the tissue, the kidney cells from the cow, and harvest the bacteria out. So to get the bacteria out of the kidney cells, we would have to freeze those animal cells, and we'd freeze them way down to minus 70 degrees centigrade. That's way colder than any of your freezers go at home. Most of your freezers probably go to about minus 15, minus 20 degrees centigrade at home. We take them down to minus 70, and then we very quickly heat them up to 37 degrees, our body temperature, and then we freeze them and thaw them 3 times. And the purpose of that was to lyse the animal cells. and it does a pretty good job of lysing those animal cells. The membranes of the animal cells will just rupture, and the animal cells will fall apart. And the reason we wanted to do it is because mycoplasma likes to get down inside of animal cells and grow down inside of there. So we had to do that to lyse them, and then we actually took the supernatant back out that had the bacteria in it, and then we cultured the bacteria out of it to look and see if there was any mycoplasma. The mycoplasma obviously survived because that's what we were looking for, and we froze and thawed them much more harshly than you all would thaw them. So I just want to make sure that if you have that expensive steak at home and you're afraid to eat it today, don't stick it into the freezer thinking that it's going to be okay to eat a week from now, because if it's scary today, it's going to be just as scary a week later, and I don't want you to get sick thinking that freezing it is actually going to lyse some of the food. But the book talks about that, or lyse some of the bacteria, and I want to make sure that you know that that's probably not the case. So the next thing we need to talk about is reducing water availability, and we've actually already talked about that. We talked about it way back when we were talking through Chapter 2, I think, but we've talked a little bit about it since then in Chapter 3 and Chapter 4. One way to do that is by adding salt, and we do that with bacon, we do that with beef jerky, we do that with other things. We also add sugar, and for most things, like your jelly, my wife loves to leave the grape jelly just in the cabinet or on the counter, and no bacteria ever grows there. The only thing that really can survive in that high concentration of sugar are fungi. Occasionally you'll get a little mold colony if it gets left open, but bacteria can't grow because it does plasmolysis on the bacteria, sucks all the water out. The other thing we can do is drying food, and you can go to Walmart or a lot of different places, Home Depot, other places, and you get a dehydration machine. Basically, it blows warm air across your food, and if the humidity in the air is not too high, it'll dry those food. You can make your own banana chips or beef jerky or whatever else you want to do if you have one of those things. And we do that to preserve food. So if we add salt, add sugar, that increases the environmental solutes. And remember that term, plasmolysis. Hopefully you remember that for this upcoming term. What happens when plasmolysis when it occurs? What happens to the cell? It tells you part of the process right there. So the water is pulled out of the cytoplasm. The plasma membrane doesn't actually lyse. That's what it sounds like. But the plasma membrane just gets sucked down. It's no longer supported by that water pressure inside of the cell. And the plasma membrane collapses down inside of the cell. And because now everything's out of whack, the salt concentration down inside of the cell and all the protein concentrations, the mineral concentrations, everything's out of whack. Essentially, that bacterium does survive, except for some of those guys that we call like Staph aureus. There's a special name for Staph aureus as far as groupings go, a descriptive name, and a group of other organisms that can grow in high salt concentrations. What's that fancy name? You got it a while ago. Halophiles. Yeah, I didn't hear what you said, Keith, but halophiles is the correct term. Basically, halo is a salt, and phile means to love, so these guys can grow. Actually, that's wrong. I almost gave you the wrong term. You got that at the same time. There's another term that you got. Sorry, I had to think about it. There's another term you got right in the same 3 sentences that's not halophiles. Halophiles actually need the salt. Halotolerant. Halotolerant. Staph aureus is a member of the halotolerant organism. It doesn't need the high salt concentration to grow like the halophiles do, but it can grow in that high salt concentration. So that's a difference between those two. The halophiles like or need, they love the salt concentration. The halotolerant are able to grow in the presence of those high salts, but they don't need those high salts. Good deal. So we can dry. Sometimes you can just add lots of salt. It'll suck. We do that too. A lot of us cure meat. We'll put meat packed in salt. There's something in China, it's called the 1,000-year egg. And I think it's because it can survive for 1,000 years and theoretically still be edible, but I don't think it's edible on day one. But they pack the outside of the egg shell with these real alkaline salts on the outside, and it does exactly what we've talked about. The alkaline salts penetrate the egg, pulls out the water, and that egg theoretically is good for a long time. It tastes like it's 1,000 years old already because of the alkaline flavor that it's got. But they're basically doing this. They're pulling the water out of that food and preserving in that way. And then you guys know this term maybe, but you probably know that second, in parentheses, term freeze drying. The scientific name, and you're going to hear this as you go through your nursing and other biological pathways down the road, is lyophilization. Many vaccines are lyophilized. Most of the time, if you're the first one to touch an ampule of vaccine, it's going to be lyophilized. And what they do is they freeze that vaccine potentially with the live organism, a virus or a bacteria. Sometimes they're killed prior to doing this, but they'll freeze them very, very cold. Again, they'll go down to minus 70, minus 80 degrees centigrade, and then they apply a vacuum. You already know that when you put your steak in the freezer, if it's in a Ziploc bag or something, a lot of times you see ice crystals on the surface of that Ziploc bag or the plastic that it's wrapped in. You've seen that before, right? What's that process called where water jumps out of the ice phase, the solid phase, and into a gas phase? There's a fancy S word. I heard part of it. Sublimation. Yeah, sublimation happens even in your freezer. Basically, the water in the ice form evaporates. Where I lived in China, it was so cold in the wintertime that it couldn't snow until it warmed up. And everything, all of the ice and snow and everything else basically disappeared by sublimation. The ice and snow were going from the solid phase to the gas phase and back into the environment again. That happens in your freezer as well. We can speed that up. We can make these vaccines or foods, whatever we're doing, really, really cold down to minus 80 degrees centigrade, and then we can apply a vacuum. We can put negative pressure on the surface of that material, and that causes the water molecules to want to jump out of the solid phase much faster than they do normally at atmospheric pressures, and we can freeze dry in that way. And it preserves flavors and fruits, and some of you may have had freeze-dried ice cream. Have you had that before? Tastes just like ice cream, right? Not really. And it's definitely not cold. Is it delicious? You like it? It's delicious. You're just being agreeable, right?
Yeah.
Yeah, okay. But we use it for a lot of different foods, and there's a place here in Temple that actually takes foods, and they've all been freeze-dried. They pack them up and they send them over to other countries that have food shortages. And again, pack them up, keep them dry. They'll last quite a long time. The shelf life is years and years, as long as they don't get moist and begin to mold. So that drying process, that freeze-drying process, stops microbial growth, but it doesn't kill the organisms that might already be in there. Have any of you been unfortunate enough to have scrambled eggs that were made from powdered eggs? You can buy like milk cartons full of dehydrated or lyophilized eggs. Did they taste okay?
You can tell that they're powdered eggs.
You could tell they were a little bit different. Anyway, the point of this is that there have been a number of people who've gotten salmonellosis from eating those dried eggs that weren't cooked well enough, because the salmonella that was on those eggs or in those eggs when they packaged it weren't killed by the freeze-drying process. And that should be intuitive already, right? I just told you, we make vaccines. If we don't want to kill the organism, we just freeze them really cold, we lyophilize them, and then they're still alive when the vaccine's rehydrated and used. So that's that process. And then the last thing here is that contamination is easy to happen. This figure is basically looking at a surgical suite, and we've got some storage cabinets over here where some things are being stored, but this is post-surgery, post-op, and I believe this is already after decontamination of this room, and then they went in and surveyed to see where organisms might be, and the patient had a Pseudomonas infection, and all of those red spots that are in the figure are showing you where contamination was found after the surgery. Some of them pretty far distance from where the surgery was actually happening. And so just keep in mind that contamination happens everywhere, and it's pretty difficult to control it. So you need to make sure that you're controlling your environment and that you're taking precautions that you need to for your patient's sake and for your sake in that environment. That's the last slide in Chapter 5. The millennium is over. And do you guys have any questions?